everybody. Today we are going to discuss the chapter Quadric Surfaces in three-dimensional analytical geometry. What are these quadric surfaces? These surfaces are actually generated by or explained by algebraic equations of second degree in three variables, say x, y, and z. This kind of surfaces represented by algebraic equation or general equation of second degree in three variables x, y, and z. These are called quadric surfaces. These are also known as conical. Hmm. These are also known as conicoid. Now over here, uh, what are the general equation? What is the general equation of second degree involving three variables? You see over here, x, y, z are three variables. So we shall have this type of expression. We shall have the expressions of x square, y square, and z square. So these are the three terms containing x square, y square, and z square. Ax square plus by square plus cz square. Similarly, we have twice fyz, twice zx, twice hxy. So altogether, these six terms, these are purely second degree term involving the variables x, y, and z. Hmm. Now we have first degree term twice ux plus twice vy plus twice wz, and a constant term d would be there. All right. So over here you can see if at least all of these coefficients can never be simultaneously equivalent to 0. So without loss of generality, if we suppose that this coefficient of x square, this coefficient of x square, if this quantity is not equal to 0, that means if we suppose that this a is not equal to 0, in that case we can divide this total expression and write this expression in this kind of fashion, say x squared then plus b by a y square, then c by a z square. Then we can write 2 into a by a yz plus 2 into g by a zx, and then afterwards we have 2 into h by a xy plus 2u by a into x plus 2 v by a into y plus 2w by a into z plus d by a is equal to 0. Now over here, in place of this d by a, if we write this expression d by a is equal to suppose d prime. Okay, if we write d by a, this d prime is equal to d by a, then this can be written as d, this last constant can be written as d is equal to 0. Similarly, we can write this coefficient b by a is equal to suppose b prime. Okay, in that case this b by a, if we write this b by a is equal to b prime, in that case we can erase this coefficient, we can erase this coefficient of y square, and we can write this coefficient is equal to b square. Similarly, you see we can erase all the remaining coefficients. We can write c by a is equal to c prime, and this can be written as c prime over here, and so on and so forth. All right, so we can erase this a, we can write a prime, we can erase this a, we can write g prime, we can erase this a, we can write this expression as h prime. In place of u by a, we can write u prime. In place of v by a, we can write v prime. In place of w by a, we can write w prime, and so on. So what you observe is that we actually have these unknown coefficients b prime, c prime, and then A prime, G prime, and how many such unknown coefficients are there? If you recall over here, initially we had three coefficients over here: x square, y square, z square. Then these three coefficients of x, y, y, z, and zx, and then these three coefficients of x, y, and z, and this constant. So altogether we had 10 unknown constants, and by dividing these unknown constants by a, we actually have all these 9 unknown constants. This can be written in this way. So in order to determine a second degree equation, we need to know 9 independent relations involving x, y, and z, so that we can determine all these 9 equations. Now out of these results over here we shall discuss that this kind of quadratic surfaces may represent different kind of surfaces in three-dimensional geometry. The first kind of surface that we shall discuss over here today in this lecture is cone. This is the surface that we shall discuss. Apart from this, in the subsequent lectures, we shall also discuss another type of surface that is called cylinder. Hmm. Then some central conicoids are there, like paraboloid, hyperboloid, not paraboloid, hyperboloid or ellipsoid. Non-central conicoid is a paraboloid, and then surfaces of revolutions are there. So different kind of surfaces can be expressed by this kind of general equation of second degree. Hmm. Today we are going to discuss this surface, this that is called cone. Now, what is cone? In general, we have the idea of cone that says, say we have this type of surface. Say this is one straight line. Say this is another straight line, and we have this type of surface. Hmm. So this is the basic idea of cone that is introduced in school level geometry. However, over here, you see this section is actually a circle, but in general, this section is not necessarily a circle. So, what is the general definition of cone? The general definition of cone says that we shall have a fixed point, this type of fixed point, and we shall have a closed curve in a plane. All right. Now, if we consider a straight line which will always pass through this fixed point, and it will pass through this curve, along this curve, as we consider different straight lines passing through this curve. In that case, altogether we will have a three-dimensional surface. Okay, and this three-dimensional surface is called cone. This three-dimensional surface is called cone. Over here, this straight line is called the generator of the cone. Generator of the cone. And this fixed point is called the vertex of the cone. And this curve is called the generating line. This curve is called generating line, not generating line. I would rather say, not I made a mistake, that it should be in the name of this curve is the guiding curve. Guiding curve. Guiding. And this straight line is called the generator or generating line. All right, generator or generating line. So these are the definitions related to a cone. Now, particularly if this guiding curve is a circle, in that case we will have the surface that is generally used or introduced in school level geometry. Okay, So this is the kind of curve, the general definition, that is called cone. Now over here you see this generator would also be extended in the negative direction as well. So in this direction as well as in opposite direction it will be extended. So the cone would be this type of surface. All right. So this is the picture of a cone. And in particular, if we consider if you consider this type of surface over here, you see, if we consider this type of surface that is introduced in school level geometry, you see this section was considered to be circle. Over here you see through the center of this circle we can draw a straight line like this, and this angle, so let us call it alpha. This angle would always be a constant quantity, and this kind of cone are actually called right circular cone. Right circular right circular cone. And this angle alpha is called the semi-vertical angle. Semi-vertical, semi-vertical angle. Okay, and this straight line, this straight line uh, passing through the center of this section of this circular section, this straight line, this section and this straight line is known as the axis of the right circular cone. So right circular cone would not always appear. In general, we will get this type of general expression of a cone. And particularly if this guiding curve is a circle, then only we will get some right circular cone. Okay, so these are some basic preliminary ideas about the definition of cone and the picture of a cone. Now let us try to understand what are the expressions, what would be the equations of a cone in three-dimensional geometry. Okay. Now over here you see we are just going to show at first that this type of general equation of second degree will always represent a cone provided this u, then this v and this w and this d, all these quantities become is equal to 0. Okay, and how to show this result over here? You see over here we can show this result in the way that that if we consider this type of equation, this type of general equation of second degree, in that case you see over here you consider this generating line. We are going to show that this equation will represent a cone passing through the origin. That means this would be the vertex 0 comma 0 comma 0. And a straight line passing a straight line, or you can say a generator passing, this kind of generator passing through this origin 0 0 0. The equation of the generator can be written as x by a, that is equal to y, not a, rather let us write l. Okay, x by l, that is equal to y by m, this is equal to say z by n. Let us write it as r, so that we can say that x is equal to l into r, y is equal to m into r, and z is equal to n into r. Now if we put these expressions of x, y and z in this equation number 1, then what we shall get? We shall get this type of expressions. You see over here we shall get this type of expression: a into l x, or say sorry, l into r whole square plus b into n into r whole square plus c into n r whole square, etc. plus twice f in place of y and z, we shall have m into r multiplied by n into r. Then the term twice g zx. So we shall have twice g zx means n into r multiplied by l into r. Hmm. And after that, what we will get? We will get mm, the term involving twice h. So l r into mr would appear. Then we shall have twice ux, so twice u into lr, then twice vy, so twice v into mr, then twice wz is there, so twice w in place of z we shall write n into r. Finally we shall have d is equal to 0. Okay, so now you see, if we further simplify this expression over here, we can take this firstly r square common, and in that case we shall have this type of expression: a l square plus b m square plus c uh, n square, plus something like this, twice f m into n plus twice g, then what we shall have n into l plus twice h into l into m, plus you see this much would be term containing r square. Then we shall have term containing r. Now in that case, you see, we shall have from this term, if we take this the twice r common, in that case we shall have u l plus v m plus w n, and then the constant term would appear. This would be is equal to this plus d is equal to 0. Now you can check over here in this in this picture. You see, this was the generator, this was the vertex, and a straight line was there. So this type of line represented by x is equal x y and z, this type of expression, x is equal to lr, y is equal to mr, and z is equal to nr. So this type of line would always lie on this generator, x is equal to lr comma mr comma nr. Okay, this type of line will always lie on these generators. So you see, this type of equation, this equation will, has to be satisfied for more than two values of r, or in other words you can say that this is actually an identity. So the coefficient of r square, the coefficient of r, and this constant term would be individually equal to 0. So this leads to this type of result, that this is the coefficient. You see, in place of L, M, and N in this book, they have taken x1, y1, and z1, whatever it is. So we shall have this type of relation. This is the coefficient, this is the r square related term, this is r related term, and this d related term. So this all these three coefficients must be is equal to 0, as because this is an identity. Now over here, if this is an identity, in that case this first term, that is actually the coefficient of r square, that must be is equal to 0. Then this second term, that is the coefficient of r, that is equal, this should be is equal to 0, and the constant term d, this should also be is equal to 0. Now what does it mean? It means that this point x1, y1, z1, okay, this point lies on a surface like this: ux plus vy plus wz is equal to 0. But you see, this x1, y1, z1, this point is actually a point on the cone. All right. So it can never be a point on a surface like this. Why? Because this surface represents a plane. This is the equation of a plane. Hmm. This is the equation of a plane. So once this point lies on this kind of cone, it cannot be a point lying on this plane. Got it? So over here, this is possible only when this type of result will be possible only when individually this coefficient of x, that is u, becomes is equal to 0. This coefficient of v becomes is equal to 0, and this coefficient of w becomes is equal to 0. Then only this total expression, left hand side expression, would be is equal to this 0. So this is the result we wanted to prove, that over here x u is equal to v is equal to w, that is equal to d. All of them must be is equal to 0. So this is the condition under which a general equation of second degree will represent a cone. So if this is the condition, then what would be the equation of the cone? We shall have this type of equation. You see, we shall have this type of equation over here. Ax square plus by square plus cz square is there, and then twice twice fyz plus twice gzx plus twice hxy would be there. But you see, this kind of equation may represent a pair of plane provided this delta, this determinant, becomes is equal to 0. But it represents a cone, so it should not represent a pair of planes. That's why we have taken this condition that delta not equal to 0. Okay, so if delta is not equal to 0, in that case we can say that this kind of general equation of second degree will represent a cone. All right, and converse the result is also true. You see over here, if you consider this type of equation with delta not equal to 0, then for any point, for any type of point like r into x1, comma r into y1, comma r into z1. These are actually points on the generator. What was the equation of the generator as per this book? X by x1, that is equal to y by y1, that is equal to z by z1, that is the r. So you see, this is any arbitrary point on this type of straight line. And what is this type of straight line? This type of straight line is actually a straight line passing through the origin. So you see, this type of straight line would always lie on an equation represented by on a surface represented by this type of equation. So we can say that this straight line would be a generator of the cone represented by this type of equation. So a cone will always this type of homogeneous equation of second degree involving three variables with delta not equal to 0 will always represent a cone. Now, you see, we are going to find out the result or the condition under which not necessarily a homogeneous equation of second degree. Over here, you see, this is a homogeneous equation of second degree. This type of this type of terms, all these terms are second degree term. No first degree term is there. So, if we have any first degree term, then what would be the condition under which this type of equation or a homogeneous equation of not necessarily homogeneous, a general second degree equation will represent a cone? We are going to find out this condition under which a homogeneous equation will represent a cone. So we have this type of homogeneous equation. We have this type of homogeneous equation. You see, well, over here we have this type of homogeneous equation, and this homogeneous equation has this type of expression: ax square plus twice b plus by plus by square plus cz square plus twice fyz plus twice gzx plus twice hxy. So this much is equal to this much is the homogeneous portion, and this much is a non-homogeneous portion. So we are going to study under which condition this kind of equation will represent a cone. All right. So what we do, we actually perform. We firstly suppose that alpha, beta, gamma be the vertex. Or of course, this is not a cone passing through the origin, so we can say that vertex cannot be the origin, because if it is a cone passing through the origin, in that case these three terms, the coefficient of x, y, and z, and the constant term, all these four terms should be equal to 0. But over here we have extra these four terms, so we can say that the origin is not a vertex. So we suppose that alpha, beta, gamma is the coordinate of the vertex. All right. Now what we do, you see, just draw this coordinates over here. Suppose this is the x coordinate, this is y coordinates, and this is the z coordinate axis. And suppose this is the vertex, and say this is the cone that we are going to study. Now this is the vertex, so over here this will be the point having coordinates alpha, beta, gamma. And now what we do over here, we now shift the origin, and we make a translation, and then we shift the origin at the point alpha, beta, and gamma. Okay, at the point alpha, beta, and gamma. So if these are the new coordinate axis, x prime, say this is y prime, and suppose this is our z prime, then what would be the relation in between x prime, y prime, and z prime? You see, x prime would be is equal to something like x minus alpha, y prime would be is equal to y minus beta, and z prime would be is equal to z minus gamma. Or you can say x would be is equal to x prime plus alpha, y would be is equal to y prime plus beta, and z would be is equal to z prime plus gamma. Now you observe that just if we drop this prime notation, so x should be replaced by x plus alpha. If we drop this prime notation, then x would be replaced by x plus alpha. That's why we have replaced this x by x plus alpha in this equation. We have replaced x whenever x is there. We have replaced this expression by x plus alpha. Similarly, we can replace the expression of y by y plus beta, and replace the expression of z by z plus gamma. And in that case, we shall have this type of expression. Over here we shall have this type of expression, and you see this would be an expression in the new coordinate system. Now you see over here we can now say that yes, now these new coordinates can also be represented by x, y, and z, dropping the prime notation. Initially we had this type of prime notation. Now we can say these are the new coordinates without prime notation. These are the new coordinates. So with respect to these new coordinates, we can say that the vertex is passing through this new origin. All right. With respect to this new coordinate system, the vertex is passing. The vertex lies on this new origin. So therefore, in this new equation, the coefficient of x, the coefficient of y, and the coefficient of z, and the constant term must be is equal to 0. All right. So in this new equation, all these terms should be is equal to 0. So now let's compute these coefficients over here. We can expand this expression. We can expand this expression, and we can write this expression in this way. This is the expression without. This is the expression ax square by square plus cz square plus twice fyz plus twice g zx plus twice hxy, etc. And this is the twice x related term, this is twice y related term, this is twice z related term, and the remaining term is actually the constant term. So you see this, all these coefficients, this coefficient, this one, this coefficient, sorry, this one. You see, so this coefficient of x must be is equal to 0, coefficient of y must be 0, then coefficient of z must be is equal to 0. All right, and therefore we can now say that these expressions, these expressions from these coefficients, you see, this is the expression, this is equal to 0, then the coefficient of y, this is equal to 0, and the coefficient of z, this is also is equal to 0, and this total this expression, this constant term, okay, this constant term would also be is equal to 0. And the interesting fact is that this constant term can be arranged in this way. You can check this constant term, okay, this constant term, this one, this constant term can be arranged in this way: alpha into this expression, the first expression, what we have, a alpha plus h beta plus g gamma plus u. Then we can write it as b into this second expression. Over here, h alpha plus b beta plus f gamma plus b is there. Then we can have plus gamma into this third expression. That means g alpha plus f beta plus c gamma plus w. All right, and apart from this, we shall have one more term, that would be is equal to u alpha plus v beta plus w gamma, okay, plus this d. Altogether, this quantity should be is equal to 0, is constant. So this is actually this is actually the second expression of this constant term. Got it? Now you see over here, as because this term, this expression is equal to 0, so you can omit this this expression, this term. Now this expression is equal to 0, so we can omit this term, and again this expression is equal to 0, so we can omit this term. So only non-vanishing contribution, that means that will ultimately come from this expression, is that this u alpha plus v beta plus w gamma plus d, this must be is equal to 0. So that is represented in the next page. You see this u alpha plus v beta plus w gamma plus d is equal to 0, along with this equations over here. Along with these equations, you can see, along with these equations, these three equations, we can also write this equation: u alpha plus v beta plus w gamma is equal plus d is equal to 0. Now over here, from these four equations, if you just eliminate alpha, beta and gamma, you will get this type of determinant is equal to 0. So this is the condition under which a general equation of second degree involving three variables would represent a cone. All right, so this is the condition for representing a cone. Now let's try to discuss the general equation of a cone containing the axis. You see, and of course, if this equation, if the cone contains the axis, that means say this is the this is suppose one coordinate axis, this is suppose another coordinate axis, and this is the third coordinate axis. So we can say that this would be a cone passing this kind of cone. Maybe this is the x-axis, say this is the y-axis, and this is the z-axis. So of course, this cone would always pass through this origin 0, 0, and 0. Okay. Therefore, this is a cone passing through the origin, and that's why it should be represented by a general equation of by a homogeneous second degree equation like this, with delta not equal to 0. Okay, and you see, if you consider the generator, then the generator must look like this, straight line passing through the origin, this kind of generator. L by x, that is equal to m by y, that is equal to n by z. And all the points on this generator must lie on this surface. What are the points on this generator? If we write L by x is equal to m by y, that is not L by x, rather I should write x by L. X by L, that is equal to m by not y by m. y by m, that is equal to z by n. Say this is equal to r. So what would be the point lying on this straight line? L into r, comma m into r, comma n into r. These are the 3 points. These are the points lying on this kind of straight line. And if it is a generator, then all such points should also lie on this cone. And therefore, if we put x is equal to lr, y is equal to mr, and z is equal to nr in this equation of the cone, we will get this type of relation. Now you can observe that over here you can observe that this x-axis is a generator. Now, in case of x-axis, what are the direction ratios? In case of x-axis, 1, 0, 0 is a direction ratio. Or in other words, you can say L is equal to 1, M is equal to 0, and N is equal to 0. This is the case when X is the generator. So if we put L is equal to 1, M is equal to 0, and N is equal to 0 in this relation, what we get? If we put L is equal to 1, on the left we have L, we have A, and you see all the remaining terms, b m square, c n square, twice fm, and twice g n l, and twice h l m, all these remaining terms would be is equal to 0, and the right hand side is equal to 0. So what we have, we ultimately find that a becomes is equal to 0. Similarly, if you consider the y-axis, you will be able to prove that b is equal to 0. If you consider the z-axis as the generator, in that case, you will be able to prove that c is equal to 0. So that's why they have directly written that a is equal to b is equal to c is equal to 0. All these terms are equal to 0. Okay, and therefore if a, b, and c are equal to 0, in that case we can omit these 3 terms, and this would, in that case, this would be the equation of a cone passing through, or you can say passing through the axis, or in which the 3 coordinate axes are the generators. So this would be the equation of the cone. All right, and it can also be proved that any 3 mutually perpendicular straight lines can be a generator. If any 3 mutually perpendicular straight lines become a generator, in that case this cone should look like this type of expression. In this expression, you see x square, y square, and z square related terms are absent. Only xy related term is there, yz related term, and zx related terms are there. So these are the three. These are few important results related to the equation of a cone passing through the axis. Okay. So this is the important result that would give us the equation of the cone passing through the axis. Now you see we are going to find out the equation of cone with the origin as the vertex or a given curve as the base point. I mean, what I mean to say is that suppose we are given a curve like this, and we are given the vertex. In that case, we will have to find out the equation of this cone. Okay, we will have to find out the equation of this cone. How to find out the equation of the cone, that I am going to discuss over here. But instead of theoretically discuss this result, let us discuss by an example. So you see, let us consider this kind of example over here. Say these are examples. So consider this type of example. Find the equation of the cone whose vertex is the point 1, 2, 3. Okay, we are given the equation of a cone having vertex at the point 1, 2, 3, and the guiding curve is the circle x square plus y square plus z square is equal to 9, x plus y plus z is equal to 0. What does it mean? It means that this circle is actually represented by two surfaces. This is the equation of a sphere, and this is the equation of a plane. So the circle is actually the plane of intersection of this sphere and this plane. Okay. Now, what we have to do, we have to firstly construct the equation of the generator. Generator is a point passing, is a straight line passing through this point 1, 2, 3. This is the vertex of the uh, of the of the cone, required cone. So we can say that x minus 1 by L, that is equal to y minus 2 by n, that is equal to z minus 3 by n. That would be the equation of the generator. Although they have written in this last expression is also there, you just add up all these expressions, you will finally end up with this last ratio. However, if you do not know, you can simply consider this one as equal to r. In that case, what we have in that case, you see x can be written as L into R plus 1, then y would be is equal to m into R plus 1, and then z would be not plus 1, it would be plus 2, and z would be is equal to m into R plus 3. So now you see we are given this expression. The this is the guiding card. So for certain value of r, a point on this straight line. You see this is the vertex and this is the guiding card. And suppose this is the generator. Not like this. Let me draw this picture like this. So this is the generator. Okay, and you see, of course, for certain value of r, for certain value of r, a point on this generator must pass through this guiding curve. In this region, the point on a generator must pass through this guiding curve. Let's see what would be the value of r for which the point on the generator is passing through the guiding curve. In that case, what we need to do, we need to put these expressions of x, y, z in this equation of the guiding curve. So what is the equation? The equation is x plus y plus z is equal to 1. So x means L into r plus 1. This is our x. Then y means m into r plus 2, and z means n into r plus 3. This expression must be is equal to the right hand side 1. So from this expression we can compute the expression of r. What would be the expression of r? R would be is equal to minus 5 divided by L plus m plus n. Okay, now if we put these expressions of r in this expression, in this value of r in these expressions over here, you will get the expressions of x, y, and z. So what would be the expression of x? For instance, suppose x would be is equal to L into this minus 5 times L plus m plus n, then plus 1 is there. So we add this plus 1. Then what we shall have, the expression of x. The expression of x would be is equal to how much? That would be L plus m, not L. That would be m plus n minus 4L divided by L plus m plus n. So this would be the expression of x, and you will get this expression of x. Okay, this is the expression of x. Similarly, you will get the expression of y and expression of z. Okay, in this way you will get the expressions of x, y, and z. Now if you put these expressions of x, y, and z in this second surface of the guiding curve, that means x square plus y square plus z square is equal to 9. Then what would happen over here if we put all this over here? In that case, you see, if we put these expressions over here, in that case we will have this type of relation, say m plus n minus 4 n whole square plus etc etc, that is equal to the right hand side 9 into l plus m plus n whole square. You will get this type of expressions. Now this is the expression obtained for a single generator. What was the equation of the generator? This was the equation of the generator. So the equation was this type of equation. Equation was this x minus 1 by L, y minus 2 by m, z minus 3 by n, and all. So over here you will have to eliminate L, m, and n. So what to do? You can suppose this is equal to some ratio r or k or whatever you write. We just considered r, so rather we can put k. So what would be the expression of L? L would be is equal to x minus 1 by k. Similarly, you can compute m. M would be is equal to y minus 2 by k, and n would be is equal to z minus 3 by k. So if we put these expressions of L, M, and n in this relation, ultimately you will find that this k 1 upon k its whole square would appear, and on both of these sides, so 1 upon k whole square would get cancelled, and finally you will end up with this type of expression. That would be the equation of the required cone. So in this way we can compute the equation of the required cone. This would be the equation of the required cone. All right. So this is the technique by which we compute the equation of a cone if the vertex and the guiding curves are provided. Now you see, in case of right circular cone, if origin is the right circular cone, in that case, sometimes it may so happen that that this is the vertex, and this is the original vertex. You can see, and this axis is provided, and a generator is provided. And in that case, if this is the same vertical angle, suppose theta, and suppose these are the equation of the axis of the cone. That means arc axis have the direction ratios A, M, N, and the generators have the direction ratios A, B, and C. Then we know how to find out the angle between these two straight lines having the direction ratios L, M, N, and ABC. So in this way, we compute the expression of on the cosine of that angle. So if we now eliminate these constants, which constants? The constants of the direction ratios involved in the equation of the generator. So over here we shall have to eliminate ABC, not element. Okay, you students make this type of mistakes. So be very careful that we shall have to eliminate the direction ratios of the generator. So A should be replaced by X, B should be replaced by Y, C should be replaced by Z over here. And so eliminating A, B, and C will get this category, this type of expression, and this would be after elimination of ABC. This would be the equation of the given cone. So this is the equation of the given cone after elimination of the direction ratios of the generator E, B, and C. And the same process can be applied if we if in place of origin we consider any arbitrary vertex alpha, beta, and gamma. Okay, so in this way we can find out the equation of right circular cone. Now regarding one result, that is the intersection of a plane and a cone. What would be the plane? The theoretical results are there. That I am not going to these theoretical results. Over here, let me discuss it in this fashion. Say this is a cone, and if a plane intersects, and the plane may intersect it in this fashion. So what would be the corresponding line of intersection? This would be the corresponding line of intersection. So we may get a pair of straight line. It may also touch the cone. So if the plane touches the cone, in that case this would be the point at which the plane will touch the cone. This might be the point at which the plane touches the cone. In that case, we will have only a single straight line lying on the cone. That means we will have a generator, or it may hardly pass through some other direction which does not intersect the cone at all. So in that case, we would not get any intersection. So ultimately, if we have a plane passing through that vertex, we'll get ultimately either a pair of straight line or a single straight line, or it would not cut the plane at all. So these are the results regarding the intersection of a plane and intersection of a plane passing through the vertex and a cone. Now, to finish this result, we consider the condition under which this kind of homogeneous equation of second degree will have three perpendicular generators. So, suppose this is the second degree equation. That means it is passing through the origin. Now, you see over here, three perpendicular generators means these are not necessarily the coordinate axis. Okay, these are not necessarily the coordinate axis. It may so happen that we have three more straight lines, three perpendicular straight lines. Maybe this is one straight line, maybe this is another straight line, and this is the third straight line, which are mutually perpendicular to each other. And the cone is passing through this type of three mutually perpendicular straight lines. Then what we need to do? We need to rotate the coordinate axis, so that these three straight lines would become new coordinate axis. So this is the x-axis, this is suppose the y-axis, and this is suppose the new z-axis. These are the old coordinate axis, x-axis, say this is y-axis, this is the z-axis. Now after rotation, this type of equation will be converted into which kind of equation? Into an equation in the new coordinate system. It will be converted into an equation in which this coordinate axis, capital X-axis, capital Y-axis, and capital Z-axis are the generators of the cone. And we know that in that case, this would be the expression after rotation. This would be the expression of the cone after rotation in terms of new coordinates. Although they have written in terms of small x, small y, and small z, actually in the equation of this new equation, the equation after transformation would be like this: L into x y plus m into y z plus n into zx, that is equal to 0. No term would be there involving x square, so we can say that 0 into x square is there, plus 0 into y square is there, plus 0 into z square is there. Now we apply the theory of invariance. You see, if we apply the theory of invariance, in that case we shall have a plus b plus c. We know that this quantity is invariant quantity. So on the right hand side we shall have the a prime, this expression, that is the coefficient of capital X square. Over here you see the coefficient of capital X square is equal to 0. So a prime plus b prime plus c prime would appear. The coefficient of capital X square, then coefficient of capital Y square, and coefficient of capital Z square, and these all should be is equal to 0 plus 0 plus 0. So that is equal to 0. So what you observe is that a plus b plus c must be is equal to 0 in order to represent this kind of equation, in order to represent this kind of cone having three generators by this type of equation number 1. Okay, so we can say that this equation number 1 will represent a cone having three mutually perpendicular generators, provided that a plus b plus c becomes is equal to 0. So these are the results involving cone. So that's all for this lecture. Thank you for being with us.